Всем добрый день. Меня зовут Георгий Кучерин, и я занимаюсь...
Hello everyone, my name is Georgi Kucherin. I am researcher of complex threats in Kaspersky Lab. Over 15 years, we are opening eyes of the society, of the community. We open their eyes to the threats we have. We also develop different projects, several projects, that help us to make the analysis of threats easier and simpler and more available. And one of such projects, this is our plugin hrtng, the IDA Pro. And goal of this plugin is to simplify and to accelerate the process of reverse engineering. But before I show you how it does it, I will tell you about this history of this plugin. We started developing in 2016 with my colleague, reverse engineer Sergey Belov, very experienced engineer. He decided to make this internal fork of Hex3 tools. That was Milan Bahachik was developing this tool over many years. They were adding different capabilities to it. They were the capabilities that we were lacking for reverse engineering. For example, deciphering data or deobfuscating the code. And the last year, we posted this project under license GPL v3 that gives the community a chance to copy the code, to change it, and to post changes they made. They can do it freely. And since we started the development of the project till we published it, many years passed, 8 years, and by the time the project was published, there were more than 40 capabilities, and now there are more of them. And now we had to do a lot of work about refactoring of the code, because such projects that are used as tools for in security, speed plays the key role. The faster you do the reverse engineering of the malware, the faster you write the report and you send it to community and they learn about it. Vulnerabilities, the faster you do analysis of the code, the sooner you'll do the proof of concept. And so the work on refactoring was quite complex. And we did it well, because when we published our plugin and we sent it to annual competition of X-rays for developing IDA, and this year this plugin won the first place in the competition. And today, to show you how this plugin can help reverse engineer, I would like all of us to analyze commercial spy software, FinSpy, and this FinSpy, in the industry of virus analysts, they know about it. There's a code of this is very tangled. There are lots of obfuscations.
Windows, macOS, Linux, iOS, Android и даже кнопочные телефоны BlackBerry. Но сегодня мы будем анализировать этот образец, один из образцов этого ПО для Windows. Итак, давайте переключимся на виртуальную машину. И вот у нас в директории наш образец. Давайте в первую очередь посмотрим на байты этого образца. Для этого я воспользуюсь утилитой hexdump. Hexdump-c.
I use utility hexdump sample, and I use utility less to bring here first bytes. And what we see here, we see first bytes 4D, 5A. These are first bytes of Windows MZ, the first bytes, and based on what we see, we deal with the file for Windows. Let's put this file in IDA. So I open it in IDA.
Выбираю директорию с
So I choose a directory with the sample.
Вот в этом окне IDA просит нас выбрать тип файла.
And in this window, IDA asks us to take the file.
Как исполняемый файл для Windows. Мы можем лишь загрузить файл как
We can take the binary file, and we don't have any choice just to do it. We press OK.
Здесь нажимаем «Да». И теперь нам нужно подождать, пока идет автоанализ файла.
Click on yes here and wait for the automated analysis of the file. Please show me the hands those of you who deals with product engineering on a daily basis. Great.
Автоанализ у нас закончен.
The auto-analysis is over.
Вот у нас байты нашего файла.
And here are the bytes of our file. 45A. When I work with the files, I always prefer to make sure if the first bytes of the file are disassembled. If we need to transform that into code, we will see assembling instruction here. So, what can we conclude from that? Our sample is not an executable file for Windows. It only comprises a raw assembling code. These files are called shell codes. And when we see such an assembling code, we should assign the flag showing that it's an executable. That's what we do for that. The editing window pops up, and we check out execute, write and read. Now, let's proceed to code analysis to analyze the code that we see, namely these first instructions. The first two instructions, if we look at them, we will see 4D and 5A. These instructions don't mean anything per se. They are only needed to disguise the executable as an executable Windows code. For instance, if it's executed by an automated utility, it's executed incorrectly. As to the other values, they have one in L register, and A is written into the stack. Now let's have a look at further instructions, namely these ones. To begin with, we see that constants are assigned here, ECX and EBX. If we go further, we will see this interesting sequence of instructions. The FLDZ and IFSENV are executed, and something is assigned to the register from the memory, like ESP10H. And we don't understand at a glance what's stored in there. That's why we need to analyze the first two instructions, and they can give us an answer to the question. FLDZ writes constant 0 to the mathematical coprocessor stack. And the second one, FSENV, allows writing the status of this component. It's minus C and minus 10. Should these values be together, we need to understand what kind of status is it. For this, we can consult the documentation for x86 architecture, where this information is presented like this. What can we do? We can transform this information into a C structure, which will look like this. Now, if we know that our status is based on ESP-1C address, we can calculate the offset of each field here, and we will find out that it contains FIP, and according to the documentation, this structure field contains the address of the most recent floating point instruction executed. This is our FLDZ of the instruction. In fact, we have the shellcode address written in order to get this address. It is the value of the LP register. Now, if we go further, we will see that 1D is added to EDI, and here we are with the following figure. We see the XOR and draw instruction here, and our encryption key is stored in BL. This is this register, and this is the value. As far as the quantity of data is concerned, here it is in the ECX register. And the operations themselves, they are operations on EDX values. If we scroll down, we'll see these weird instructions with unclear constants. They mean nothing. It's just rubbish. What can we do about them? We can define them as just data. If we look at those data, we will see just random bytes. And we can conclude that it's something encrypted, and the decryption takes place here. In order to go on with our analysis, we need to decrypt what's used by the malware, and it can be done in different ways. Some people do it with IDA Python scripts. Some other people download decrypted data to the disk to come up with a third-party program which can be C-based, for example, or it can be based on any other language. Today, we will be decrypting with the use of Lavina hrtng. hrtng. It uses a lot of encryption algorithms that are used by the malware. Besides, this feature is heavily integrated with IDA. For instance, if we need to specify the encryption key which is stored inside the analyzed file, we can only specify the file. It will be retrieved and perform the decryption. Let's see how it works in practice. To begin with, we will select all the encrypted bytes, Alt plus L, and here we are in the end of the encrypted payload, and we can define this payload as an array. We click on Shift plus asterisk, and here we click on Enter, and here we are with the array. We're in the very beginning of the array. We right-click and select Decrypt Data. In this pop-up, we have to select our encryption algorithm. The algorithm is called Custom. By the way, it's very easy to add your own algorithm. You open this .cpp and add the implementation of the algorithm based on C or C++. And these two lines represent our algorithm. What's next? We need to specify the number of bytes to be decrypted. The plugin automatically retrieves it from IDA, and we also need to tell the encryption key. We saw it before in the EBX repository. Register. We click on OK, and the plugin suggests that we write the decrypted data to the database. We do it, and now if we transform this array into data and define it as code, we will see decrypted instructions. And we can continue now analyzing the code. Here, the instruction is analyzed that's responsible for this transition. If the AL is not 0 and GNZ is 0, we are switched to this instruction. If we scroll up, we will see that the register has the 1 value. Then we move here and then here. And here we are with another assembling code, and we have to note the first 3 instructions. Move ADI, push EBP, and nov EBP. They are the forward of the function. We can define those instructions for our function. We click on P, and now we can decompile the code. If we look at what we have here of interest, we will see this function, A9D8. Let's dig into it. We see that the second argument is a pretty large number. Besides, if we look at what's returned by the function, we will see that it's a pointer to another function. Look, v32 is used to call another function. Now, let's look into this function. We'll immediately see some work on structures that regulate this 03C and 038 offsets. If you have worked with Windows executables, you will immediately recognize these offsets. 03C is used to get another offset for the E header, and 078 is used to get an offset for the export area. And here we see some work on P file headers. Now, if we scroll down, we will see this function here, A924, with this small algorithm with a constant ED to 8,320. You should remember it, memorize it if you're engaged in re-engineering. E32 is used for caching, so if you enter this constant, you will immediately understand that it's about 32. Therefore, in our executable, we have some action allowing to work on headers and calculate the hash sum. If you have an analyst with reverse engineering experience, they will immediately understand that API hashing is used here. This technique is about calling API functions or library functions in a concealed manner without mentioning them in the code. It works as follows. For example, we want to call this function anti-protect virtual memory. For this, we compute CRC32, and during the runtime of the malware, we do iterations for all API function names. We take each function name and calculate its CRC32 hash. And we do it until we come up with a function having previously computed hash, which is 0x70417. Which means that we have identified the address of the required function. This technique is quite often used by malware. That's why we provide for a capability to counter it efficiently. Our plugin also implements algorithms that are heavily used by malware, such as Murmur 32 and others, and I'm going to demonstrate how this feature can be used. For this, we return to the function with these huge values. These are our hashes. Now we click here and select Turn on AP hash stun. Here we go for CR32 and click on OK. And now
библиотеки типов данных,
we need to import data type libraries that are used by Windows.
Shift плюс F11,
We click on Shift plus F11 and then insert
пишем MS-SDK
and write MS SDK
Win10. Так называется
Win10.
MS-SDK.
This is the name of the MS SDK library, and we need to import it with native API functions. We click on Insert and enter NT-API
Win10.
underscore Win10.
Это сделали. Мы можем
Once we've done it,
обновить.
we can click on F5,
Если мы
refresh our decompiler, and with this we'll see that the names of our variables have been changed for function names, which can be called with API hashing. What else is important? IDA, by using plugin, has managed to restore the number of function arguments. It's a very convenient technique. Having done that, we don't need to look into the documentation again in order to understand what's done by argument 3, for example, in our function.
Давайте посмотрим дальше, что делает эта функция.
Let's go further to find out what its function does. And we'll see a very interesting cycle here,
Сравнение поиск сигнатуры.
which is about comparing to find a signature.
MZ и P.
We see that they are MZ and P signatures. You should read these names in a reverse manner,
файлах.
which is the signature of one of the headers in the P file.
Вначале.
Let's remember, we have already seen this MZ signature.
У нас это первый
We know
инструкция.
that these first bytes
Это MZ.
are our initial instructions with MZ. If we scroll down,
То вот мы видим наши байты PE.
we'll see
Вот эта сигнатура
our
PE,
P
которая
bytes,
переносом.
which means that it's a P signature which is being looked for by the malware. What can we do? We can try and understand,
Что-то еще.
is it really a P header or something else?
Чтобы это
And
сделать,
we mentioned P headers before.
заголовков IDO.
We need to import IDA to the structure of P headers. We click on a structure. Here we push on Insert, Add Standard Structure, and here we enter
Headers.
image underscore NT,
Это такое название у Windows PE заголовка.
which is the name of P headers in Windows.
Дальше мы нажимаем
Then we click on OK,
Q и
then Alt plus Q,
структуру. Мы видим, что
and select the structure.
изменилась наша структура к
As you can see, our structure has been applied to the bytes.
на значение этой структуры, которая
And if we look at the value of the structure, which is being loaded,
что
we will see
вполне себе здесь валидные данные, это никакой не мусор,
that we have valid data here, it's not rubbish, which means that the structure was applied
то
correctly.
есть у нас происходит при помощи этого файла загрузка
In other words, with this file,
в память.
we download
Так как у нас
our,
это и получить.
we load our malware sample to the memory. Since we failed to achieve that with IDA, now we have to do it manually.
Чтобы это сделать, нам необходимо два шага исполнить.
For this, we need to carry out two steps.
Этот наш
Firstly,
ископаемый файл, это
we need to load our payload to the correct address. And this address
и он называется
is in the file is called image base.
у нас поле image
And I'm going to show it to you now. This is our image base field, and here is its value, which is 4000.
адресу 0. Нам
And
нужно
now we're going to send it to the 0 address.
segments, rebase program.
We click on Edit Segment
Я беру и вставляю
and simulate
значение
program.
4000.
And I copy and paste this value here. And now we have our correct loading address.
У нас API функции
Now we need to
используются
understand
нашим образцом вредоносной программы.
which API functions are used by our malware sample.
И файлов, которые называются
Usually this information is the structure of P file headers is called import directory. I'm going to demonstrate it to you right now.
листнем ниже.
If we scroll down,
мы здесь видим поле структуры, которое называется Data
we
Directory.
will see the structure field that's called data directory. There are 16 data directories like this. The one that's of interest to us has index 1. These indices are 0, and here is index 1.
124.0c.
And this number 124.0c is used as an offset in the memory for the import information structure. It's called relative virtual address.
Эту информацию мы должны
In order to switch to this information, we need to add to our base address this particular number, 124C.
получится что-то вроде 4.
We do it, and that's what we expect
Вот у нас информация
for
о
1240C. And here is our import information.
импорте. Я вам
Before we get down to analyzing it, I'd like to show you some trick
смещением.
which will help you to switch between these offsets with no computation,
Адреса.
to make them clickable as addresses.
Со структурами.
For this, we go for structures
Определение структуры Image Data Directory.
and see
В ней
how our image D directory is defined here.
таки в ней содержится это смещение.
And the virtual
Ctrl-R.
address
Yes.
is exactly what we need.
У нас
We click on yes here, and here we are with this window. We need to make sure that this line is chipped out. Use image base as offset base. We click on OK, and once we've done that, we see that our IDA has marked our structure field with the offset RVA comment. Now, if we return to IDA,
стало кликабельным.
we will see that this offset has become clickable.
На этот адрес нажать и
We can click on this address
это
and get information about imports.
массив структур, которая
This information is an array of structures that are called import descriptors. In other words, we carry out the same
файла. Мы открываем
actions that we carried out with the API file header.
добавить структуру
We go for structures, click on Insert,
structure
Add Structure,
и выбираем image
and select Image underscore Directory. And again, image underscore import,
descriptor.
and import again underscore descriptor. And here we are with our descriptor.
Дело с массивом дескрипторов импортов. И мы должны вот эти вот байты превращать в структуру дескриптора.
And here we're dealing with the descriptor imports.
Полностью нулевыми значениями. Сейчас
And then we need to get a structure with all the 0 values. And let me tell you what it is. Let's we click Alt Call
здесь не нулевые значения.
and we change the structure and we see there are non-zero
То
values.
же самое.
And we do the same
Мы не встретим полностью нулевую структуру.
until we see fully null structure, zero structure.
Импортов.
There are many of them.
И вот у нас дескриптор с полностью нулевой
And here
информацией.
we have a descriptor with a completely zero information. In these structures, we have information about those library functions that we get from the information system, from the operation system. And now let's compare the result that we received with what is written in the documentation on the executable files of Windows.
Если мы посмотрим на
If we
структуры
look
дескриптора импорта,
at
то мы
the
увидим, что его первое
structure
поле,
of
original first thunk,
Windows, we can see that the first stump
на имена
will show you
функций.
the names of imported functions. But in our case, for some reason, instead of information about the names, we have zeros. There is a question why.
Здесь стоит напомнить, что мы
And here it's worth mentioning,
со структурами PE файлов.
yet we are dealing with the PE file structure. This example is not purely executable file, PE file.
Злоумышленники что сделали?
It's a shell code, and what the hackers did,
Структуры импортов
they purposely
с файлом работать.
damaged
Она
the
не находится в первом поле
imports.
структуры. Она находится
And information about imports not in the first field of the structure, it's somewhere else. In order to understand where it is, now we need to analyze other fields of the structure. the ones that are not 0. That's the last and the one before the last. And these are fields. This is offset in the memory. Let's repeat the life hack that we did before. Let's do the structure. So we have image descriptor. We Control R, yes. We have window in which we see use image based is on, and we click OK. The same we do with the last one of field of the structure, Control R. We see that the tick is there, and we see it's OK. Then, if we look at what's in the fields, we can see that everything is OK with the previous field. There should be a name of the library that the function is imported from. But if we look at the last field, then we'll see some unclear data. And the last field is called hrtng. It should have addresses of the functions. We put the address of the function that we get from the operation system as a result of processing imports. But if we try to define this information as 32-bit value that is equal to the size of the addresses, then you can see IDA defines these constants. It assigns names of the functions to them. If we open a different field, here we also see the pointers to different functions. Here we can see types. And what we are dealing with here, as I said, the structure of imports are damaged, and malware uses a non-standard algorithm of downloading in order to determine imported functions. These constants that we saw before, there are CRC 32 hashes from the names of the functions. We can see here at AT hashing technique, and what the loader does, they take a number, each hash, and they determine what function matches this hash. And instead of hash, it writes the address of the function. Let me show you how it works. So let's launch as A5C44C50. So the loader decided that this is a hash equal to anti-query information process, and this number is overwritten as address of this function. The same with the other functions, so the number and overwritten, number overwritten, and so on. hrtng. So when we started to rewrite in this as constant, we were automatically restoring the names and types of arguments. We can see the functions that are behind the numbers, restored names and types of arguments. Now, when we finished downloading the executable file, so what to do with its point of entry? So it's the first user's function that is executed when PE file is downloaded. Then offset in the memory to this function. It is in PE title, and it's called address of entry point. Let's try to find it. Address of entry point. Address of entry point. Here it is. Here's the number. We use the same life hack. We put it to the clickable address. We take the field of the structure. We find image optional header. This is what contains the address of entry point. We Control R, yes. We see that the check is there, and we click OK. So we move to the address. So if we're dealing with the function, so it's proper to see it in function. We click P, and we can see that IDA colored the addresses here. Our numbers in red, which means He didn't manage to define this instructions as functions. And to understand what's the problem is, we need to determine the code of the function. And what's interesting here, we see that the values of the registers ESI and ECX, they're like this. And then we see with ESI registry, they do a lot of mathematical operations, adding, deducting, multiplying, many of them. If we get to the end of these operations, so we list it, we can see that after they're executed, we have the values of the registers ESI and ECX. There are some very strange operations done, and then the value ESI just taken off from the stack, and as a result of mathematical operations, we lose it because it's not used anywhere. And that's why these operations are not needed. They were added to the code as garbage in order to obfuscate the tools of analysis. And what we need to do, we need to signal to IDA that these functions don't do nothing. So, and then we replace it with an OP function. And in our plugin, there is a very convenient function for that. We take all the garbage instructions that go from the beginning of the instructions. We do Alt-L. First mathematical operation, SBB. So we scroll it to the end to highlight all of them, the operations that we don't need.
Вот у нас закончились операции.
So operations are over. And what we do? We click Edit, Fill Knobs. We click OK, and here instructions are replaced with knobs. When we deleted the garbage code, then it gets to this instruction. If we see what's written there, then we see here the couple of conditional transitions and many others. Let's look at these transitions. We can see that they go in couples, in pairs. In each pair, the transitions are opposite. G, Z, if they jump if 0, G and Z, J and Z if not 0. So what we can see in each pair, each transition refers to the same instruction. So in fact, we're dealing with the fact that one of these two conditional transitions always executed, and the address of the transition is the same. To execute one of these instructions is to perform one of these transitions. So, and what realization here? This technique is called obfuscation. So that IDA could not create a function here. So, and such obfuscations are called obfuscations of control thread, and so you can find them. Find in our code in hrtng, we have the capabilities that help us to get rid of these obfuscations. Let me show you how it works. We go to the beginning of the function and we click the Alt F5. We have a window. We click OK in it. It analyzes ranges, and as a result of the analysis, there is an error. The plugin writes to us, we need to create an instruction at this address and try to compile it again. We click OK, and the plugin opens us the address of the instruction that incurred the problem. That's some garbage code. And let's see where this code is used. We click on X, and here's the use of the code. So what do we see? We see what's in the argument of the function, and it's compared with the in the registry EAX. And here is the assignment in EAX. It zeros the value of the registry, and then there is increment operation. So in AX we have 1, and the value of the argument is compared with 1, and if it's not equal to 1, then we jump to garbage. Again, this is something unneeded and not needed, and this is technique of obfuscation, technique of analysis. So we do the same. So we highlight the instructions, we click Edit, Patch Program, Fill knobs. We click OK. And then we try to decompile the code using the function hrtng. And then we have the code that can be actually read. The analysis of the code is not simple, so if you spend some time, then you will realize, consulting with the internet, that here we see the obfuscation engine, FinSpy VN. And it's based on the technology of virtualizing the code. And technology is that the code on the architecture x86, it turns into some exotic architecture of the processor that is invented by the authors of the malware. To obfuscate virtual machines, this is a very complex challenge, and how it's done, we're not going to study today because there are special articles about this, about how to deobfuscate FinSpy VMs, and if you're interested in how to do the deobfuscation, so you can consult with them. And we today will use the script we already have, the one that is used for deobfuscation. But there's a nuance here. You know, for it to work properly, you need to fill out these blanks, and you need to compare names of virtual instructions with their identifiers, with their opcodes. I will show you what it means. Codes of these virtual operations, they are stored in this table. This table is a table of pointers to function, and each function realizes some virtual instruction to x86. Let me show you. If we take this instruction with index 1, index 0, index, I decompile it, and here we see the operation with the offset tool to the left. So this is realization of instruction offset left in our virtual architecture. And since this instruction virtual, and we have index 1, and we write here that's a virtual instruction of shift left equals 1, and we have 30 like this virtual instructions that we need to recognize. And we need to do it because in each example, the order of this instruction is random. So you can't just do it. You need to repeat the operation for each sample. Here are the functions, and you need to somehow recognize the names of the functions in order to fill out this table, this class with numbers, how to recognize functions in binary code. We know how to do this, and there is a default engine, it's called Flirt, and it allows you to do that, but there is a nuance here. It is based on assembler code, and if this assembler code is obfuscated, and if you change a couple of instructions in it, then signatures, recognition signatures, they stop working, and functions can be defined in our hrtng plugin, we have special engine that uses microcode. It's an interim, some pseudo code. This is used for decompiler. It's more optimized, therefore it's more stable, working with obfuscation. It's very simple to use this engine. First, you need to take the sample that was analyzed and need to export information from it about names of the functions and their recognition signatures, and then you upload these signatures to IDEA. Let me show how to do it. I have a file with signatures. I click File, Load File, msig file. I go to directory. Here is the signature. And now, if I decompile the code, I can see that it says there was a function as a shift to the left. If I look at this function with index 2 and I decompile it, virus will be GB. If we go back, then we see that the name's changed, and in our code we can note that jump if below it equals to index 2. And we do it like this to all instructions, because we have auto name recognition, so it's very easy to do. It will take some time, we're not going to do it now. So we use the ready script that we already got ready. So script file, I go to the directory where I have the script, and I apply the script. Now, let's look at the point of entry function. After the script was run, I decompile it again. And when I do it, I can see, let's page it down, we have a pretty clean, non-obfuscated code. And let's see what it does. We see different functions in it that uses API hashing, and what we can understand about the functions. Here, different functions of working with the network, the function of working with files, create file, functions working with key of the registry. Here you import the whole class of functions that work with messages. They use it for key logging in the malware. Besides that, there are some funny lines here I'll show you. For example, here, this line, GNU PG. And based on the information about the lines and time, we can make conclusions what it does. It's implant that is used for cyber spying that can could steal PCP keys and many other things. And in order to analyze this file, we did a lot of actions. We started with deciphering the code, then we switched to API hashing in order to deobfuscate the entry point. In order to deobfuscate the virtual machine, we recognized the function. We did it so fast due to our plugin hrtng. And you would agree that without the actions that we did with the plugin, so all this work would have taken many, many hours that you had to spend to script. And I think that with this example, I hope I convinced you that hrtng plugin will help reverse engineer a lot. And before I start answering questions, I would like to thank Sergey Belov wholeheartedly, my colleague who created and who is the main developer of plugin hrtng. Without his great job, I wouldn't be able to present this plugin to the community. So please use the QR code and download the plugin. I hope it will be useful in your everyday work. Thank you very much.
Друзья, у нас стоят микрофоны, так что не
We have microphones here,
за лучшие
so you can ask your questions. For the best question, you will get a book. Thank you for the presentation. It was really interesting. The question is how hrtng helps in dynamic unpacking of codes to the memory. How it, when it unpacked and it does jump to the memory.
Спасибо за вопрос. Если
Thank you for the question. If I understand it properly, so we opened the sample and debugger of IDA, and we need to do the unpacking so that all the results of unpacking will be in IDA. And there are many functions in this plugin. It is there. There are more than 40 functions, and this one exists there. It's very useful, and I use it myself. So, I mean, if I have a buffer, can I do the inject of this buffer to the code? With like you use the nope. Inject of the buffer.
Кстати, сходу это нужно конкретный адрес указать, где он на диске. Я думаю, здесь лучше воспользоваться
You can just
скриптом. Это в одну строчку делается при помощи функции.
Patch script, you can do a patch batch, and that's how it is done here. Here, colleagues with a question. Hello, my name is David. In your opinion, for the reverser who just begins, for the beginner, should they work on the code on their own and or to automate it? I think yes, it's worth using this one because these actions, the API hashing, deciphering, they're of a medium and hard level, and if beginner is just beginning to analyze the malicious code, for them this actually can be quite useful instead of looking for something on the internet and you realize when mistakes. And I know what I'm talking about because when I came to Kaspersky lab and I didn't have a real experience in reverse engineering of malware, I started using this plugin and it helped me a lot. Thank you. Thank you for your presentation, very interesting. I have two questions. First one, how did you choose the engine for the demonstration? And then, either the binary ninja, is there something similar? Because there is a big API and there are many different presentations of it, so maybe it would be interesting. Thank you for the question. The engine was very easy to choose because in the compiler it's just it's microcode. There are no alternatives. What we have embedded in IDA, it's very convenient. There are many different levels of maturity, and what we do, we take the last maturity level where the code is optimized, and we calculate signatures. What about binary ninja? Yes, in the compiler, it has intermediate presentation. It's even more useful to look at, more convenient to look at it than in IDA. I don't know how recognition works there in binary ninja. One more?
Почему у вас используется IDA, например, а не Hydra или Binary Ninja?
Why do you use IDA but not Hydra or Binary Ninja? We use everything. We use everything. Hydra is used when we need to analyze the code on the architecture that is not realized in the compiler of IDA from Spark. We don't have it in IDA, and we use Hydra, and it depends on the tool. And you can also decompile with Hydra, but for this one, I prefer IDA. So you use this plugin IDA Pro on IDA Free too, only for IDA Pro. Either Free does not support it. Thank you for your talk. A lot about your company. How often do you use symbol execution for automation. Do you have any instruments of that? Yes, we have these tools. We use these tools and we don't use them because, first of all the operations we can do it simpler. We use it with a plugin and with almost automatically. And symbol execution can be quite slow. Sometimes analysis works very slowly, and it takes time. So I personally don't use it. On a GitHub, such tools, there are many of them. We can see what you can look what Anger can do. Georgi, thank you very much for your presentation. It's a lot of technical details. Just amazing that you showed everything in live examples. Could you choose the best question that will give the book for? I think the first question was the first one because it was more technical. And also, if you didn't manage to ask your questions here, so Anton will tell you, now we're going to have the project fair, and our project is presented there. You can come to us and you can ask your questions about the project and about reverse engineering. So right after that, we have the open project fair, and you can come to the speakers, and Georgi will be there, so you can ask him all the questions you want. Thank you.